So, let us continue the discussion on the Ramjet, and we are looking at the individual modules first, like we have looked at intake and the burner. Now, we are looking at we are going to look at nozzle and then finally, the complete engine analysis. So, how would the nozzle, again the nozzle would look like, let us say draw a schematic of the nozzle. It may look, let us say like this. Here is some portion here. So, again this is A and B, which is used as a inlet and exit. So, the TS diagram for the nozzle module, this would be A to B. So, this is B. So, this is BS, this is OA, so this is let us say we get OB, and this portion is BB square by 2CP. And if I draw the again the block diagram, let us say the nozzle, here is the nozzle, it has nozzle efficiency of eta n, exit velocity, VB exit temperature, inlet T naught A, P naught A. Again A is inlet, B is outlet. Now, what happens then, eta n is T naught A minus T naught B by T naught A minus T B S, and what we can do, T B equals to T naught A 1 minus eta n 1 minus P B by P naught A gamma m minus 1 by gamma m minus 1. So, and we get the exit velocity is 2 CPM T naught A minus T naught B. Here CPM is the mixture specific heat, because now this is after the bond product. So, we use that. Now, let us say if nozzle is a convergent type and choked, then the Mach number at the exit is sonic. So, exit condition would be critical one, then the ratio between the total temperature to the static one would be T naught A by T critical, which is gamma plus 1 by 2, and the nozzle efficiency that time could be calculated T naught A minus T critical by T naught A minus T naught TBS, 1 minus TCR by T naught A, 1 minus TBS by T naught A, which is 1 by 2 gamma plus 1, 1 minus PRC by or PCR by P naught A gamma minus 1 by gamma m. Now, and critical pressure ratio, we know that this would be P naught A and pre critical would be 1 by 1 upon 1 by eta n gamma m minus 1 by gamma plus 1 gamma m by gamma minus 1. So, this is what the critical pressure ratio is. So, now you see why the discussion of compressible flow and all these relationships are important, because this is what going to be handy. Now, with that we move ahead with the complete engine. Let us say we draw an engine like that, something like that. Then so then there would be nozzle. So, here things are at the exit, these are the hot. Then we have this portion for the inlet, this is called the diffuser. Then we have here, let us say somewhere fuel is injected, this is the burner. So, we call this one as the combustion chamber, and then this portion we call it nozzle. Now, we have different zone, let us say A1, then we got it 2, 3, 4, 5, 6. Now, A21 is supersonic compression, 1 to 2 subsonic compression, 2 to 3 fuel inlet, 3 to 4 combustion, 4 to 5 or rather 4 to complete 6 is the expansion process in nozzle. So, and if you put a sort of an block diagram to that, then it will look like an, let us say you have intake where you M1 comes in, T1, P1, this is where your M dot A goes T02, P02, this is combustion chamber where you inject fuel and then it comes out T04, P04 goes to nozzle, it gets T6, gets V6, and in between there could be, so can go there. So, this is the complete block diagram. Now, once you have the block diagram, then you can always put the cycle. Let us say we can put the TS diagram. Let us say TS diagram, what happens will go here, this is A, then this is 4, then we come to 6. So, this is 02, then this is 6, this is 04. So, this is an ideal TS diagram where P naught A is P naught 2 is P naught 4 equals to P naught a P6. So, that is a ideal situation. Now, in realistically that would not happen, because you will have this oblique shock or shock boundary layer interactions which will take place in the intake. There would be losses, and that loss will also continue, and that is why the actual cycle would be slightly different. And if you plot that actual cycle, let us say if this is the point and this is the point of 0,2. So, this is P naught 2, and so instead of this is A, this is P naught A. Okay. So, the actual one comes here, and then you go also to this is 0,4. Okay. So, the actual is the dotted. So, it comes here, and so this is P6, this is 0.6, and this is P naught 6. So, this would be, so here these lines which are dotted lines. Now, the actual one differs from the real one, and that because of some of these losses which takes place. Now, first we will start with the ideal cycle. Now, when you look at the ideal cycle, this is the previous TS diagram that we have. What will have that the ideal cycle, the pressure, total pressure is constant in the cycle. So, P naught A is P naught 2 is P naught 4, which is P naught 6. Okay. So, since no work nor heat addition or rejection takes place in the intake and nozzle, so we can apply the first law of thermodynamics. So, what we will get, T naught A is T naught 2 and T naught 4 is T naught 6. So, that is what we get. Now, nozzle is assumed to be unchoked. So, then the full expansion of the hot gases within the nozzle to the ambient pressure is assumed, and therefore, we will have P A equals to P 6 equals to P exit. Now, we can write down the all the total and stagnation condition between 6 and E. So, what we will write, T naught A by T A is 1 plus gamma A by 2 m square, which is T naught 2 by T A, and T naught exit by T E, which is T naught 6 by T 6, 1 plus gamma 6 minus 1 by 2 m E square equals to T naught 4 by T E. And similarly, we can write for the pressure P naught A by P A, which is 1 plus gamma A minus 1 by 2 m square, gamma A by gamma minus 1, P naught 6 by P E, which is 1 plus gamma 6 by 2 m E square, gamma 6 by gamma 6 minus 1. So, these are the stagnation condition that we can write. Now, what we also have P naught 6 by P e is P naught A by P a. So, we can arrive at the relation at that. So, can get M e is m. Though the inlet and exit Mach numbers are equal, but the exit speed is not equal to the flight speed. So, what is clear that u v is A e by E, which is gamma 6 r t exit by gamma A r t a into u. So, if you assume gamma r to be constant within the engine, then u exit would be T exit by T a into u. So, now we can replace that with the temperature. So, we can get this is T naught 4 by T naught A into u, which is equivalent to T naught 4 by T naught 2 into u. Now, we can find out the fuel air ratio in the burner or the combustion chamber. So, there we will use the energy balance equation, which is m dot A H naught 2 plus m dot A q r equals to m dot A plus m dot F into H naught 4, where q r is the heating value of fuel. But what we have T naught 2 is T naught A. So, we will get F equals to C p 4 T naught 4 by C p 2 T naught A minus 1 Q r by C p 2 T naught A minus C p 4 T naught 4 by C p 2 T naught A. Now, for constant gamma r within the engine, F boils down to C p T naught 4 minus T naught A Q r minus C p T naught A. Now, we get the thrust force. Now, now since the nozzle is fully expanded, so that is P e is P a. So, what we can get is that T equals to m dot A 1 plus F u e minus m dot A u, or T by m dot A is 1 plus F u e minus u, which is 1 plus F u e by u minus 1 into u. Now, we can use another relationship, which is u e use T naught 4 by T naught A, which is u T naught 4 by T a by T naught A. So, u T naught 4 by T a root over 1 plus gamma minus 1 by 2 m square. So, the thrust force can be expressed, which is m root gamma T a 1 plus F T naught 4 by T a 1 by 1 plus gamma minus 1 by 2 m square minus 1, and T s f c this could be m dot f by t, which is f by t by m dot a. So, these are the situation what you will get from the ideal cycle. Now, in the real cycle the things will deviate, and there, because there would be nozzle like intake, there would be losses which we need to take into account. Then the combustor, there would be little bit of pressure loss because the combustion efficiency may not be 100%, there would nozzle, there would be losses. So, what would happen that when we look at the real cycle, now we have to have different pressure ratios or the stagnation pressure ratio, like let us say in the diffuser you have R d, which is a pressure ratio which is called P naught 2 by P naught A. Then combustion chamber, it is R c, which is P naught 4 by P naught 2. Then we have nozzle, which is let us say R n equals to P naught 6 by P naught 4. So, these are the stagnation pressure ratios that we can define, and the overall pressure ratio is P naught 6 by P naught A, which is R d into R c into R n. So, that is the overall pressure ratio. But the properties gamma r, as it pass through the different portion of the engines, we can still assume constant. So, now what we write that stagnation pressure at there is gamma minus 1 square by gamma minus 1. So, what we get from here, P a by P naught a gamma minus 1 by gamma into 1 plus gamma minus 1 by 2 m square is 1. Similarly, P naught 6 by P 6 we can write 1 by m e square by gamma minus 1. So, we get 2 by gamma minus 1 P naught 6 by P 6, which is 1. So, we can write 2 by gamma minus 1 into 1 plus gamma minus 1 by 2 m square, P a by P naught a gamma minus 1 by gamma, P naught 6 by P 6 minus 1, which is 2 by gamma minus 1 plus gamma minus 1 by 2 m square, P naught 6 P a P 6 P naught a gamma minus 1 by gamma minus 1. So, this can be written that exhaust Mach number is 2 by gamma minus 1 plus gamma minus 1 by 2 m square R d R c R n P a by P e gamma minus 1 by this. Let us say we define this quantity is completely something equivalent to m, then we can write 2 by gamma minus 1 into m minus 1. So, that is what you can write. Okay. So, also if R d R c R n is 1, P equals to P a, then we get m equals to 1 plus gamma minus 1 by 2 m e square. So, which essentially means m e is m. Okay. Now, the heat, if the heat transfer from the engine is assumed negligible, then the exhaust total temperature T naught 6 would be T naught 4, and what we can get is that T naught 6 by T 6 and T naught 4 by T exit 1 plus gamma minus 1 by 2 m e x square. So, we get gamma r T exit, gamma r T naught 4 T by T naught 4. So, this is m e gamma r T naught 4 1 plus gamma minus 1 by 2 m e square. So, this is m e gamma r T naught 4 by m. So, we can also see that from here we get that these things is this. So, now what we can write, this is m. Now, substituting this, what we get, u e is 2 gamma r T naught 4 m minus 1 by gamma minus 1 m. So, irreversibilities, they have no effect on total temperature throughout the engine. So, we can find out the fuel air ratio for the real Cp 4 T naught 4 minus Cp 2 T naught A by eta B Q r minus Cp 4 T naught 4, and the specific thrust F u e by. So, we use that u equals to m root gamma t, then this guy becomes 1 plus F 2 gamma e r T naught 4 m minus 1 gamma minus 1 m minus m gamma r T a plus P e a e by m dot a 1 plus P a by P e. So, that is the specific thrust expression. So, this can be derived, and so if you look at the picture, like if I plot T by m dot a versus m, so this is how thing would. So, this is increasing T naught 4, this is the actual ideal cycle, and the actual cycle would be like this for both the cases. So, this is ideal one and this is actual cycle, how it look like. Similarly, if you see that TSFC versus Mach number, so this is how it look like. This is again, so increasing T naught 4, and this is how the actual cycle would work. So, this is also T naught 4. So, you can see how the specific thrust and TSFC, they vary between actual and ideal cycle. So, one thing is clear here, that when you consider the actual cycle, one need to calculate or take into account the losses and irreversibilities which take care, and then the actual cycle always deviates from the ideal one. But it is good to see the ideal one first, because that short of a special case of the actual one, when all the efficiencies and everything becomes unit and all this, but realistically there are losses. And so, we will continue this discussion in the next class from here.